Today on Calculus, we're going to be working on section 6.2, day 1, and this is our first proper look at the definite integral. So let's get started over on the next screen. George Friedrich Bernhard Riemann, 1826 to 1866, was a German mathematician who made contributions to analysis, number theory, and differential geometry. In other words, those mathematical skills that you would be going to do in a collegiate level course. In the field of real analysis, he is mostly known for his first rigorous formulation of the integral, the Riemann integral, and his work on Fourier series. His contributions to complex analysis include most notably the introduction of Riemann surfaces, breaking new ground in a natural geometric treatment of complex analysis. His famous 1859 paper on prime counting function, containing the original statement of the Riemann hypothesis, is regarded as one of the most influential papers in analytic number theory. Through his pioneering contributions to differential geometry, Riemann laid the foundation of mathematics of general relativity. He's considered by many to be one of the greatest mathematicians of all time. And with that kind of a resume, I think you could probably see why. Just as kind of an aside here, we are looking at mathematics from the mid-19th century right now. And for most of probably your mathematics career at this point, you were looking at things done by ancient Greeks, ancient Egyptians, the ancient Indians, and earlier. But now we're getting into some really contemporary things. 1866, if you think back to American history, that's really not that long ago. So we're going to go ahead and start here with a review of what we did yesterday, or in the last lesson, which were Riemann sums, but we didn't call them Riemann sums. We called them left rectangular, and right rectangular, and midpoint rectangular approximations. Those are examples of Riemann sums, not because they approximate area, but because of how they were constructed. So let's take a look at construction of a general Riemann sum. We're going to use this function as an example, the one that we have graphed over here on the right. And the first thing to know is that the Riemann sum creates an approximation, a partition of the function by dividing the interested portion into a number of subintervals. So we're going to be looking at 4 subintervals, and I think I'm going to color code them, and I'm going to make them pretty regular for our work. Over here, we have intervals that I did as an example. And down over here is what you as a student should be writing, but I'll work as a student and not as the teacher in this case. So your partition doesn't need to be regular, although the one I'm going to do is going to be regular. So it doesn't have to be all the same width. And I don't think that mine is going to be all the same width either. So let's go ahead and highlight my subintervals. So here we have it color-coded. My first subinterval is the yellow subinterval. And that's going to take care of all x's between 0.2 and 0.5. Next, we have the blue subinterval from x equals 0.5 to x equals 1. The green subinterval is from 1.0 to 1.5. And with our final subinterval from 1.5 to 1.8, we can kind of move on, although we're going to be referring back to this graph. So, with the construction of the Riemann sum, what the next thing we're going to do is we're going to identify a place inside each subinterval, and we'll call that place C1, C2, C3, and C4. When we did the left Riemann sum, we chose our C's to be the left side of the interval exclusively. And when we did a right midpoint approximation, we chose our C to be the right endpoint approximation. But for any Riemann sum, you can make that C you can evaluate the function any place. So let's see. Let's make the first one maybe 0.3. So that will be 0.3. The second one, let's put it over on the left side. No, let's put it on the right side. Let's make it right over here at x equals 0.9. C3, let's put it, let's put it all the way over on the right side at 1.5. And C4, let's put it right over here, that 1.6. So you can see we're evaluating the function at any general place. It doesn't matter where, as long as you evaluate it someplace in the subinterval. And then we're going to draw next our rectangles. So here we've drawn our rectangles. The width is the width of each of those colored subintervals. And the height is the height at C1, the height at C2, the height at C3, and the height at C4. Now, the Riemann sum is related to the area here, except for instead of finding the actual area, what we're going to add together is the function evaluated at Ci multiplied by our delta x's. So for the first, let's do the red rectangle here. The function evaluated at 0.3, so f of 0.3 is about negative 0.2, so the area of that first rectangle is about negative 0.2 multiplied by the width of the yellow rectangle, which is 0.3. The next rectangle, we chose to evaluate the function at 0.9. So we're going to do f of 0.9 multiplied by the width of that, which was 0.5. The third rectangle, we chose to evaluate at 1.5. F of 1.5 is approximated at 0.4. So the area of the rectangle is f of 1.5 multiplied by the width of the green rectangle, which was 0.5. And that is going to be 0.4 multiplied by 0.5. The last interval, we are choosing to evaluate our function at C4, which was 1.6, giving us a height of 0.35. Going over here, we're adding all of those rectangular areas again. And you'll notice, look at the yellow one. That has a negative value for the function. Area can't be negative, so in essence, although this calculation is going to be similar to area, or it's going to have something to do with the area, strictly speaking, this Riemann sum is not equal to the area. Oh, what does all of this add up to? For me, when I add up all of those rectangular pieces together, I get of 0.425. So my Riemann sum is 0.425. So that's how we construct a Riemann sum. It has to do with the rectangles and just adding a bunch of rectangles together, basically. The rectangles themselves, again, are defined by a function, and we can evaluate the height of the function at any place in the subintervals that we choose. So here are some observations. If the entire function is above the x-axis, then that Riemann sum is going to be an approximation of area. However, we had one rectangle where we evaluated the function below the axis. And in those cases, where the function is below the axis, we get a negative approximation of area. So if the area was 0.06, we get a negative 0.06 for the Riemann sum. It's the area, but the negative of the area. For functions that are above and below the axis, what we're going to get is the area above the axis minus the area below the axis. So it's a difference of area, I guess we would say. So here we go with getting to calculus finally. If we increase the number of subintervals, say we go to infinity, then the Riemann sum more closely approximates the area and or the exact areas. And if we let our delta x go to 0, then we're going to get the following limit. So there's some strange notation here. I'll try to talk you through it. So the first one is the limit as what we say is the norm of p. Let me highlight that for you. The norm of p goes to 0. And the norm of p is just going to be the longest subinterval. So we're saying the biggest subinterval that we have, that width is going to go to 0. And then we're going to add up all of the areas of the rectangles. So we see f of c multiplied by delta x. Delta x is the width of the rectangles. F of c is the height of the rectangles. So here what we're seeing with the sigma fc delta x, that's it. We're adding together all of the rectangles. So we're adding together an infinite number of rectangles where the width of each rectangle is approaching 0. Strange. This is kind of like what I like to call the mysteries of calculus. The area of each individual rectangle is approaching 0, but we're adding an infinite number of rectangles. So if we add up an infinite number of things that are close to 0, we get a number that's called I. And I is the definite integral. It's going to be the exact area of the area above the axis minus the area below the axis. And I'm going to say it again. It's the exact area. So again, with the mysteries of calculus, we add together an infinite number of zeros and we get area. It's crazy. Most calculus veterans will recognize the integral if we write it in this form over here that I've highlighted. The integral is equal to, and it looks like a swooshy S, a narrow and swishy S, from a to b. We always read the lower limit first, the a to b of f of x dx. So this is the integral from a to b of f of x with respect to x. If we correlate the parts of this integral to the limit of the sigma becomes the integral sign. And I guess it kind of makes sense on some level because, the sigma is the Greek letter for s, and the integral is kind of a swoopy s. F of c becomes f of x, and that shouldn't be that big of a deal, f of x, f of x. And the delta x becomes dx. And this is something in calculus. Delta x is a small change in x. Dx is a very, 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 very small change in x. So delta x and dx are really the same thing. It's just in calculus we call the delta x dx to signify that we're going from small changes in x to infinitesimally small changes in x. So it's a change in magnitude, in scale, I guess. Next we have a definition of the different parts of the integral. Of course, the s is what we call the integral sign. The number at the bottom, where we have an a, this is the lower limit of integration. The number b on the top, we call this the upper limit of integration. And we always read from lower to upper, so from a to b. This over here, the function, this is what we call the integrand. So it is whatever it is that we're integrating, that's our f of x. Over here with the delta x, that is our variable of integration. And that kind of is all the parts of the integral that we need to talk about. The dx, again, comes from the delta x. It is the width of the rectangles. Not only is it the width of the rectangles, it tells us the variable that we're integrating. So there's a few things that are kind of wrapped up in the dx. I feel like most students just kind of say, oh, the dx is there, just leave it alone. But it really does tell you something important, and you'll really find that this tells you something important once you get into multivariate calculus. So that was a lot of things that we just did right here. At the most basic level, though, I want you to think of the integral as a function of area. So for the integral, we're just going to take a look at the graph and we're going to compute the area, and that's the same thing as the area, as the integral. So we'll do this first one. F of x is equal to 4. Let's look at the graph of part of number A. So here's the graph of y equals 4. We're going to integrate from 0 to 5. So just a shaded region. And the area of that shaded region it's a rectangle with a base of 5 and a height of 4. So the area of the rectangle is 20. Therefore, the integral from 0 to 5 of 4 dx is also 20. Let's take a look at the next graph. It is a graph of x minus 1 from negative 2 to 3. Now in this case, we're going to have to consider two different rectangles, or two different triangles here, because the first one is going to go from is going to be the negative rectangle. It's going to go from x equals negative 2 to x equals 1. So this is what we would call our negative triangle because it's below the axis. Notice that the triangle goes from x equals negative 2 to x equals 1. And then we have another region above the x-axis, and this one goes from that negative 1 all the way to, oh, and I think I went too far. We were only supposed to go to 3. When we find the area this time, and when we find the integral this time, we'll need to consider this negative area. So our integral is going to be two triangle area formulas. Examining the two rectangles, we've got the blue rectangle with a width, a base of 3, and a height of, and I'm going to call that negative 3 because it's below the axis. And we have the yellow rectangle with a width of 2, the base of 2, and a height of also 2. So the integral evaluates to negative 5 over 2. Even though the area isn't 5 over 2, the integral evaluates to negative 5 over 2. Finally, we have this cosine function, and let's take a look at the graph of that cosine function. So this next one is probably making you feel very nervous right now because it has a cosine in it, and you're thinking to yourself, but hey, wait, for area, I don't know how to find the area under a cosine function. So trust it. Look at the graph, and what do you know about those areas between pi over half and negative pi over half, and the area from pi over half to 3 pi over 2? Those two areas are actually the same. We've got one area above the axis and another area below the axis. So we have positive area in blue, negative area in red, and we have the two areas are equal to each other. That should be enough for you to convince yourself that the area, the integral here, is actually equal to 0. There are so many integrals here in calculus that you can do just by looking at the areas and, basically outsmarting the problem because you're looking at the graph rather than trying to figure it all out analytically. So let that be a lesson. Always try to look at the area. Now, I'm also a really strong believer that you should be using your calculator more than you are. So I'm going to teach you how to use your calculator to calculate integrals to find area. Let's start with letter A. We have the function y equals x squared, and that this is bound by the axis, the x-axis, and the graph of x equals 2. Now we have the really nice graph of this. The region is bound above by y equals x squared. It's bound below by the x-axis, and it's bound on the right side by the line x equals 2. This area is 8 over 3, and let's go ahead and compute that with a calculator. So the magic button is in two places here. Now the first place, if you have a color edition or if you have the black and white edition, actually both editions, with the latest firmware update, you just need to push alpha and window, and you will see something that says FNINT. If you push that, that's going to give you an integral, and you just need to fill in the blanks. Now, if the other way to get that same integral is to push the math button and take a look at number 9, it's that same FNINT. So there are actually a couple of different ways to get the integral. And I'm going to just fill in the blanks in the templates. That's 0 to 2, and then we have x squared dx. Now this calculator, the TI-84, will only give you the value of a definite integral. So if you're looking ahead and asking, hey, can my calculator just flat out find the integral? The answer is no. The only thing the calculator will do is find the area. So this will give me 2.667, which is, of course, 8 over 3. Little known, and it should be more known, that it is, if you want to force these answers to be fractions, you can push math, go to number 1, and it says arrow fraction. That means turn my answer into a fraction. And that will give you an 8 over 3. So you can impress your friends with that one. This next one is e to the x from -5 to 0. So we'll do the same thing here. I prefer going math 9. For some reason, my fingers work better that way. We're going to go from -5 to 0. Then we're going to put e to the x, which is second natural log. That's just to the west of the 4 button. E to the x dx. And this one won't turn into a fraction, so I'm not even going to try. The exponential function here, e, definitely fractions are few and far between. So I'm not going to bother, and I'm just going to say that that's 0.99326. Okay, not a whole lot to do here. We know that you're doing with this with a calculator, so there's no need to write the words, I did this with my calculator. Obviously, the instructions say to use your calculator. Let's do letter C. It's x cubed minus 2x squared minus 3x. Now for this one, I kind of want to show you something different here. Let's go ahead and take that function, go to the calculator, and put that function in the y equals menu. Once you have it in the y equals menu, sometimes it's easier to go to the home screen and fill in for this. Oh, but wait, I don't know where to start and where to end. Maybe I should look at the graph instead. Let's clear this off and look at the graph. So zoom 6 gives me the standard window. And I should see the cubic function shape here. Yeah, there's the cubic function shape. And I've got some area above and some area below. And the question says to find area. It doesn't say to find the integral. It says to find the area. So I'm going to actually have to compute this in two different pieces. Now the first area is going to be this loop that's above the axis here, and the second one is this loop below the axis here. Now, having factored this, I know that this is going from -1 to 0, and this is going from 0 to, what is that, 3? From 0 to 3. Now, from this screen, it is possible for you to integrate as well. So you can go second, calculate, and notice number 7 is an integral sign. So we'll push 7. The lower limit, and you can just type it. That's another shortcut here. We can just type -1. Upper limit, we can just type 0. And that will give me the area is 0.5833. Go to the home screen. And let's see, what will it give me if I do exit? No, it won't give it to me. So what was that, 0.5833? Let's pretend I didn't remember. And we'll integrate that again. So math 9 from -1 to 0. And here you can also put y1. So you can go alpha trace y1 dx. And then let's turn that into a fraction because that's impressive. That's 7/12. Okay, here's my 7/12. When you write this, make sure you're putting the integrand in parentheses, especially if there is more than one term. Otherwise, your mathematics looks like a mess. Next, let's go from 0 to 3. Just for fun, I'm going to go back to the graph, and I'm going to do the integral from 0 to 3 right now. So second, calculate the integral number 7 from 0, then type the number 3, and it's going to shade that in, and it's going to give me -11.25. So -11.25. We'll do that again. Notice that it did evaluate that integral as negative. So this area below the axis is -11.25. We'll do that again in the home screen as well. And I'm going to call up that function and just change the limits here. Just kind of backspace over to it and get me to change this to a 0 to 3. And that gives me -45/4. On your paper, don't fake it. You know that that integral is -45/4. Don't make it positive at 45/4 because that's just going to be wrong. I've seen students do that. The question is for the area, not for the integral. And the integral is a necessary step to find that area. All you need to write at the very end here equals 7/12 plus 45/4, which is 71/6. Don't make your integrals evaluate to be positive when they don't. Okay, so make everything a mathematical equality. So that was quite a bit. I'm looking at our clock right now, and this brings us to important ideas. Let's go ahead and get our important ideas out of the way. The integral is a quantity related to the area between the curve and the x-axis. It is the area above the x-axis minus the area below the x-axis. There is a symbol and a whole set of vocabulary that comes along with this. Of course, we already kind of reviewed that, so there's no need to be redundant here. And then on your TI-84, you're going to use the FNINT function in order to evaluate integrals. While we're at it, let's just go ahead and put that sigma definition over here. So we will have that. And that's really it for our important ideas. Let's try to get this over here, where we're going to take the integral of x sine x dx. We're going to shade it, and then we're going to find the value. So let's shade this the best we can. Remember, the area is going to be between the curve and the x-axis. That's a little bit sloppy, but what can you do? The next is we're going to find the area, or the value of I, which is the integral. Now, this is not a basic geometric shape, so we're going to have to rely on our calculator to integrate this for us. On our calculator, we'll do alpha window, and we're going to number 4, function integrate, and I believe it was -1 to 2, and the function was x sine x. Make sure the parentheses look correct, dx, and that gives us 2.042. And that really does it for us. So that was our first look at integrals. Integrals are going to be a big part of the second semester of calculus, if you are doing this in the second semester. Yeah, you'll definitely learn techniques for doing this so that you're not dependent on your calculator. In fact, most of your calculus teachers want you to be not dependent on your calculator to find integrals. But as we are defining them in terms of area, right now it's okay for us to look at our calculator every now and then to find the areas for more complex regions. So I'll see you guys later. Have a good one.